using completing the square for inverse Laplace transforms. In the previous video we ran through inverse Laplace. In this one we're specifically looking at the denominator within these equations. In this case you can see that in the denominator we've got an expression in a completed the square format. This is a nice format because as you can see we've got a few different options we can use for this. If I rewrite this equation with the 81 in a number squared format, you can see we have 9 squared. We can pull out the information that a equals 6 and b equals 9, and then put it into the f of t format, which will give us e to the 6t sine 9t, all multiplied by the unit step function. Nothing new really, but what if we don't have the denominator in a completed the square format? Determine the inverse Laplace of this expression. We can see that this doesn't clearly resemble anything from this f of s format. And we have coefficients for this s and this s squared, so we need to eliminate these. For the numerator, we're going to have the inverse Laplace. Taking out the numerical factor from the numerator, we can see that the coefficient of s is 2, so we're going to take out a factor of 2 from the numerator. So take out a factor of 2, and that will leave us with s minus 2 on the top. In the denominator, the coefficient of s squared is 7, so we can take out a factor of 7 from the denominator, which if we take that out, we're actually taking out a factor of a 7th. This will now leave us with s squared minus 4s minus 5. It's in a format we can work with a bit more now, so let's change the format of the denominator by completing the square. If you can't quite remember how to do completing the square, I've put a link with how to do it at the end of this video. We now have 2/7 of the inverse Laplace of s minus 2 over s minus 2 squared minus 9. And if you want, we can simplify this even more. So we have 2/7 of inverse Laplace s minus 2 over s minus 2 squared minus 3 squared. We can now pull out our values, highlight which pair on the table we need to use. Well, it's either going to be this one or this one. The difference being is this sign here. So we'll either add a constant squared or minus a constant squared. In this instance, we're minusing a constant squared, so it must be this bottom one here. I'm going to pull out separately these a and b values. So the a value is, well, we've got minus a here, so minus a equals positive a, so minus 2 must mean that a is positive 2. In the table we can see we've got this minus b squared, and the minus b becomes positive b, and here we have minus 3 squared, so b must be positive 3. Pulling all this together now, we can input this into our f of t function. F of t equals 2/7 of e to the at, or e to the 2t, cosh of bt, or 3t in this instance, multiplied by u of t. Six questions for you to try before we move on to the second half of this video. Pause the video and resume when you're ready to see the answers and move on. Here's where it gets interesting and a little tricky, so we're going to need to do a bit of algebraic manipulation for this. You can see the expression here of s plus 1 over s minus 3 squared plus 16, which currently most resembles this one and this one. However, looking at the a values, we can see in the table that we've got minus a and minus a here, or minus a and minus a here. They must be the same. However, in our expression, we have positive 1 and minus 3, so we have different values. As a little algebraic manipulation trick, if you add 1 and minus 1, you're going to, in essence, net 0. You're not going to add or take away anything. If you add 2 to something and take away 2 to something, it's actually not changing anything. So adding 5, taking away 5, we're still adding or taking away 0. So if we add something and then do the inverse, we have the original value. So if I said, for instance, 7 plus 1 minus 1, that would equal 7. 7 plus 2 minus 2 equals 7, and 7 plus 5 minus 5 equals 7. This doesn't feel like it adds any value because technically it doesn't change it, but we can use this aspect to help us solve these kinds of equations. Before we continue, let's highlight the table to say which one we need, And because we have a plus 16, it must be this one. Using that little trick now, we need the numerator to be s minus 3, the same as this. So if we want s plus 1 to become s minus 3, with the chains going from plus 1 to minus 3, what's happening is we're taking away 4, which gives us f of s equals s plus 1 minus 4 all over s minus 3 squared plus 16. But what's happened here is we've actually got a different expression from the original. So using our trick, we've got minus 4 here. So to balance this out, we need to add 4. This may look a bit strange now, but look what happens if we just simplify this a little. We have f of s equals, we have s plus 1 minus 4, which simplifies to s minus 3. Then we have a plus 4 left over. All of this is over the denominator still, which is s minus 3 squared plus 16. Because we now have the s minus 3 in both the numerator and the denominator in the correct parts, but we have this plus 4 to deal with, we're almost there. If you remember your basic fractions knowledge though, you can actually split the numerator up into 2 sections. So we can write this as f of s equals s minus 3 over s minus 3 squared plus 16, and then plus 4 over s minus 3 squared plus 16. So we still have the same here as we do here. It's the exact same because we took away 4, but we also added 4. So nothing really changed, but we just manipulated the algebra a little to get what we needed to. So on the yellow side here, we've got it in a format that works for us. I'm actually going to change these 16s into a format that's better. Looking at this, we can see it now accurately corresponds to this part here. So let's deal with this yellow part first. We have a, which equals 3, and b, which equals 4. So that will give us f of t equals e to the at, or e to the 3t, cos of bt, or 4t. And now we have to deal with this part here. With this one, we're actually going to be looking at this pair. Pulling a and b out, we can see we have a, which equals positive 3, and b, which equals positive 4. Then doing the inverse Laplace for this, we can see we have e to the at, or e to the 3t, sine of bt, which is 4t. All of which is being multiplied by u of t, the unit step function. Let's have a go with a second one that's trickier. You can see we've got this denominator that's already in the completed the square format, which is nice, but we've got this s minus 5 and s minus 7, which are different. So because the numerator, we want s minus 5, so rather than having minus 7, we want to have minus 5. We need to add 2. So what will happen is we'll add 2 and minus 2. Writing this out, we have f of s equals s minus 7 plus 2, but because we've added 2, we also need to minus 2. So this plus 2 minus 2 nets 0, meaning we add or take away 0 from inputting this. So we'll get the same outcome. And this is all over s minus 5 squared plus 9. We can break this part up from this part because they're in the numerator. Then we have this minus 2. Working with the green part first, we can see that this is the one we'll need to use. We have a equals 5 and b equals 3. This will give us f of t equals e to the at, or e to the 5t, cos of bt, or 3t. And now for the orange side, which is a bit different because we have this so far in a format that doesn't quite fully appeal to any of these. The closest it does appeal to, though, is this one. we need a way to make this numerator 3. As before, we currently have 2, and we need to make it 3. So we need to multiply this 3 by something to make it equal to 2. Well, if we're multiplying it by 3, then actually if we divide it by 3, that will eliminate the 3 because 3 divided by 3 is 1. Then all we have to do is multiply by 2 to get back to 2. So 3 times 2 over 3 equals 2. So this is the factor we can take out in order to leave 3 at the top. Which another way of showing this is 2, replacing that with 3 times 2 over 3 over s minus 5 squared plus 3 squared. And then we'll take that 2 over 3 out, which will leave us with 2/3 multiplied by 3 over s minus 5 squared plus 3 squared. So this is now in a format we can use this for. Pulling out a and b, we have a is 5 and b is 3. This will then give us an end result of 2/3 multiplied by e to the at, or in this case 5t, multiplied by sine of bt, or 3t. And finally, we have altogether f of t equals the first part minus, because we had minus here, 2/3 e to the 5t sine 3t. And that is our final answer. Slightly trickier, but manageable with a bit of practice. So give these questions a go, pause the video, and resume when you're ready. The next video dials into partial fractions. If you also need a reminder of how to do completing the square, here is the link I promised earlier in the video. Stay safe and healthy, and I'll see you in the next video.